Okay, sample diploma board problems. Which of the following types of radiation will have its path deflected by a perpendicular electric field? Well, to be deflected by electric field, you need to be a charged particle. So alpha and beta are charged particles, but gamma is not a charged particle. So that makes, A the correct answer. To balance reaction 3, the numerical value of A, B, C, and D is, so if we want to balance reaction 3, we got to be careful of this coefficient in front, right? There's 2 hydrogens, so sometimes I just put, like I read it like that, instead of putting that coefficient in front. Right? So we want the top number to equal 6, and the bottom number to equal 4. We got 6 on top, 4 on the bottom. So these numbers are easy because, well, they have to be. Hydrogen has to be 2, and, helium has to be 2, and hydrogen has to be 1. So those bottom numbers are going to be 2 and 1. But those top numbers, they can vary, right? So hydrogen could be 1, and helium could be 4. Right? That's a possibility. The other possibility is helium could be 2, and then hydrogen could be 2. So hydrogen being 2 isn't that crazy, and that would equal 6. But helium being 2 is going to be less likely. You just have 2 protons together with no neutron spacing. So it's more likely that it's going to be 4, 1, and 1, and that's going to be our answer. So it's going to be 4, 2, 1, 1. So this one is just sort of a reaction chain kind of question. We're looking for match each box number above to the daughter nucleus represented below. So we start off with lead 212, and then we do a beta negative decay, right? So that's going to bring this to 83. This is going to stay at 212. And then we'd have to look up what 83 is. So 83 is bismuth. Right, and if I take my bismuth and I do an alpha decay, which is 4 and 2, then the top number is going to drop by 8, or drop to 208, and the bottom number is going to be 81. And 81 is thallium. If I do a beta negative decay, then it's going to go up to 84. It's going to stay at 212, and 84 is polonium. And I just have to do one of these. I can check them either way. But if I do an alpha, that's a bad alpha, 4 and 2, so my top number is going to drop to 208, and my bottom number is going to drop to 82, and 82 is lead. Okay, so bismuth 212 is 1, lead 208 is 4, polonium 212 is 3, and thallium 208 is 2. Okay, so when balancing the nuclear reaction above, the physics principles used to determine values of A and B. So this top number has to do with mass or nucleons. So it's a law of conservation of nucleons. And then the physics principle used to balance C is going to be the law of conservation of charge. So A is the correct answer. Which of the following row identifies the energy of gamma photon relative to the energy states of the new isotope and the source of the electromagnetic radiation that is most similar to the method that produces the gamma photon? Okay, so this is sort of like that question that we talked about yesterday. You have your difference in energy states, right? So the energy released is from that excited to unexcited state, and comparing it to something that produces EMR, something dropping down from higher to lower states would be a hot, low-density gas that just gives out specific frequencies. So that C is the correct answer, right? It's kind of like when you heat up hydrogen and then you look at it through a spectroscope, you see those specific frequencies. This is only going to give off certain specific gamma frequencies, as opposed to a hot solid, which gives off all the frequencies. Which of the following equations describes the decay of cobalt-60? So cobalt-60, blah, blah, blah. The cobalt-60 decays by emitting a beta-negative particle and a gamma photon. And you have to know that anytime you have a beta-negative, that you're also going to give off the neutrino. So these ones are beta-positive, so those wouldn't work. And then you have beta-negative goes with the anti-neutrino. So that makes B the correct answer. Which of the following equations most likely describes the neutron to lithium collision? Okay, I'm going to have to read more. Okay, so one way to harness the energy of the Earth is to use nuclear fusion. One of the problems in terrestrial fusion reactions is that very high energy required to overcome the electrostatic repulsive force. A particular reactor uses magnetic fields in the process called magnetic confinement. However, neutrons escape magnetic confinement, so the neutrons captured are shielded by a lithium blanket. Okay. So, which is most likely describes the neutron-lithium collision? So, okay. Okay. Well, if I look at these answers here, you can see that just based on the neutrons don't have a charge and they have a mass. So that eliminates those ones. So it's basically a neutron colliding with lithium-7 or a neutron colliding with lithium-4. If I look on the periodic table, let me open my periodic table here. Right, if I look at lithium, the most common isotope is lithium-7. So it's more likely that this neutron comes into contact with the lithium-7, so this is more likely. Yeah, that's pretty much it. The neutron produced in the fusion reaction escapes magnetic confinement because a neutron is neutral, so it wouldn't be affected by a magnetic field. Yeah, A. And that is it. So this lesson is on fission and fusion, the two types of nuclear reactions. So compare and contrast characteristics of fission and fusion. Compare the energy released in a nuclear reaction to energy released in a chemical reaction on basis of energy per unit mass. Relate qualitatively and quantitatively mass defects, so that's a term you need to know, of the nucleus. And we got to use mega electron volts as well. So if I have 5 2-kilogram balls, what is the mass of all 5 balls when I put them together? So this is 2, this is 2, this is 2, this is 2, this is 2. I add up the mass, 10 kilograms. Nice and easy. Right? But if I have 5 protons, and this is their super specific mass, what is the mass of the protons when I put them all together? Well, you think you would just go 5 times 1.6726 times 10 to the negative 27 kilograms. If I did that, let me open my calculator. Just waiting, there we go. If I did that, so 5 times 1.6726 times 10 to the negative 27, you would end up getting, oops, didn't mean to do that, 8.363 times 10 to the negative 27, right? Wrong. What you'd get is you'd get a little bit less than that. You would get like 8.359 times 10 to the negative 27. You always get a little bit less mass than you would expect. So individual protons by themselves are heavier than when they're in a group together. So where does all that mass go? Why does mass disappear? Well, it's easier for a proton to be by itself. It doesn't attract or repel anything, but you have to remember that these guys are all repelling. There's that electrostatic force that pulls them away. So something needs to keep them together, which is our strong nuclear force, and that strong nuclear force energy needs to come from somewhere, and it comes from that mass. So what we call that difference in mass is we call that a mass defect. So the theoretical mass being different from the experimental mass is called the mass defect. So whenever you put a bunch of protons together, they want to repel each other. So what keeps them together? Oops, jumped the gun with that. It's our strong nuclear force. That energy for the strong nuclear force must come from somewhere, so it comes from mass. So the energy that holds the atom together is called the binding energy, and mass being converted into energy is physics principle number 6, which is conservation of mass energy. Okay, so let's do an example. So given the experimental mass of helium-4 nucleus is this. So this is the actual mass that it is. Calculate the mass defect in binding energy of helium nucleus. So we know that a helium nucleus has, it's an alpha particle, 2 protons, 2 neutrons. So I'm going to take this, I'm going to multiply it by 2. I'm going to take this, I'm going to multiply it by 2, and I'm going to add them together, and that should get me my theoretical mass. How heavy should they be? So I'm going to go 1.6726, yeah, times 10 to the negative 27, times 2. And I'm going to add that to 1.6749. Neutrons are a little bit heavier, times 10 to the negative 27. And I'm going to multiply that by 2. So my theoretical mass of my helium nucleus should be 6.695 times 10 to the negative 27 kilograms, right? But when I see my experimental nucleus, it's just a little tiny bit lighter. So if I subtract that lighter mass from it, I can find my mass defect. So my mass defect is going to be minus 6.443 times 10 to the negative 27. Right, there's 2.52 times 10 to the negative 28 kilograms missing. So that must be where the energy comes from. So to figure out, so that's my mass defect. So to figure out my binding energy, that's the energy used to hold it all together, I'm going to use physics principle number, what did I call it? Physics principle number 6, which uses E equals mc squared. So if I take this mass and I multiply it by the speed of light squared, I'll be able to find out my binding energy. So I take this, I multiply it by the speed of light squared, and I get the energy, the binding energy that holds it together is 2.268 times 10 to the negative 11 joules. Oh, I'm bad at boxing stuff. That's my binding energy. Okay? So by themselves, they're always a little bit heavier than when they're together. So most subatomic masses are given in this unit of mega electron volts per c squared, and because their mass is so tiny, the kilogram isn't a great way to express it. So if we took the mass of a proton, 1.66 times 10 to the negative 27, we can convert that into mega electron volts per c squared. Okay? So the first thing we have to do is we have to convert this to energy. So again, I'm going to use E equals mc squared. So if I go 1.66 times 10 to the negative 27 kilograms, and I multiply it by the speed of light squared, I can figure out what this would be in joules. 1.66 times 10 to the negative 27 times the speed of light squared. And I end up getting 1.494 times 10 to the negative 10. So now it's in joules, and from there, I can convert my joules into electron volts. Remember, we did this before. We know that 1 electron volt equals 1.6 times 10 to the negative 19 joules. So 1 electron volt, oops, I guess I didn't need electron volt, equals 1.6 times 10 to the negative 19 joules. My joules will cancel out, and then I'll be in electron volts. So you got to take my answer, and I got to divide it by 1.6 times 10 to the negative 19. And I get this. But I want it to be in mega electron volts, and mega is times 10 to the 6. So if I move the decimal 1, 2, 3, 4, 5, 6, right? Then I'm right there. So this would be 933.75. Oops. 933.75, and that's mega electron volts. Okay? But it's mega electron volts per c squared, and lots of you won't like this, but you have to remember that with E equals mc squared, to find mass, it's my energy divided by the c squared, right? So kilograms is my mass, so my mega electron volts it's like my energy per my c squared. So this is the units that we do. So you just throw the c squared on there, and it's not a unit, right? It's not like meters per second squared or anything like that. It's just my energy divided by c squared. That's it. It's just like a convention. Don't worry too much about it. Just throw that on there in the end. That's all you have to do. So let's do a board question. So a positron has a mass of 0.511 mega electron volts per c squared. Find its mass in kilograms. Pause it, give it a go, see if you can do it. So first thing, we have 0.511 mega electron volts per c squared. So a better way of writing that to start off is 0.511 times 10 to the 6 electron volts, and just leaving out the c squared. And then we want to convert our electron volts into joules. So what we would do from there is 1 electron volt equals 1.6 times 10 to the negative 19 joules. And then these cancel out. And then once we have it in joules, we have E equals mc squared. We want to turn it into mass. So we'd move our c squared down below. So we take this, whatever this answer is in joules, and we would divide it by 3 times 10 to the 8 meters per second squared. Okay. So I'll do that in my calculator. 0.511, make sure you include that mega, times 10 to the 6, times 1.6 times 10 to the negative 19. And then we divide by 3 times 10 to the 8 squared. And you end up getting 9.08 times 10 to the negative 31, which means that, yeah, right, our positron is 9.11 times 10 to the negative 31. And there's rounding in there, which makes it tricky to be spot on, but 9.1 kilograms, it's pretty close. The missing mass. So the missing mass is converted to energy and used as a strong nuclear force that keeps atoms together. In a nuclear reaction, the atom decays into a more stable atom. So during the reaction, the energy is not converted back into mass, but released, right? When you're more stable, you need less of a strong nuclear force to hold you together. So it's not like they convert that back into mass, they just release it into energy. Right? So this energy can be used to power cities or destroy them through nuclear weapons. So in 1938, Enrico Fermi was bombarding uranium with neutrons trying to produce an element greater than atomic number 92. But instead, when the products were analyzed, it turned out to be barium, which is atomic number 56, that he produced instead. So Fermi had split the uranium atom in a process releasing energy and more neutrons. So this was the reaction that happened. And this is a reaction you should be somewhat familiar with. This is taking uranium, shooting a neutron at it, splitting it in half, releasing energy, and very importantly, releasing 3 more neutrons. So this is a little visual of it, right? You shoot the neutron at it, it splits in half, turns into baryon and krypton, and then 3 neutrons. So when a large atom is split into smaller nuclei, it's called nuclear fission. Fission and fusion are such close words, it's kind of annoying. So when we take a large atom, we split it, it's called fission. So when Enrico Fermi found this, the world was entering World War II, and the race began between Axis and Allied powers to try to harness the atom's tremendous energy and create the first nuclear bomb. So Fermi joined the Allied Manhattan Project, which did create the first nuclear bomb. So when fission occurs, it releases huge amounts of energy due to the products being more stable, and whenever fission occurs, the products are lighter than the reactants. So that's important. That's something you need to know. So let's do an example. So the production of free neutrons caused an uncontrollable release of energy, which led to the first atomic bomb. Determine the amount of energy released from this reaction. So it gives us a whole bunch of masses of all these different things, and it gives us our reaction here. So if I want to find the energy released in the reaction, what I need to do is I need to find the mass of my reactants, and then find the mass of my products, and this is going to be lighter, this is going to be heavier, and that difference in mass is converted into energy, and that's what you would end up getting that energy from that difference in mass. Okay, so it gives us a mass of uranium in atomic mass units, and it gives us the mass of the neutron here. So I'm going to take 235.043903 atomic mass units, and then 1.008665 atomic mass units, and I'm going to add those together. And then for my products over here, I have to take my barium, which is 140.914412. Let me write that a little bit nicer. 914412 atomic mass units. My krypton is 91.926156 atomic mass units. And I have 3 neutrons, so 3 times 1.008665 atomic mass units, and that's going to give me the mass of my products. Okay, so let's do that in our calculator here. So I'll go 235.043903. I'm going to add that to 1.008665. Okay, so this would have an atomic mass of 236.052568. Okay, and then I'm going to do the same thing. I'm going to take 52568. Yeah, I'm going to take the mass of my product. So 140.914412. I'm going to add it to 91.926156. I'm going to add on, put that in bracket, 3 times a neutron. Right, and I get just a little bit lighter. Right, so now what I need to do is I need to find the difference in mass. So I'm going to take my reactants, I'm going to subtract my products, and we find that our change in mass, this is our change in mass right here. But right now it's in atomic mass units, so 0.186005. And this is in atomic mass units. So if we want to find energy, that's got to be in kilograms. So we can take our conversion factor. We want to convert atomic mass units to kilograms. So 1 atomic mass unit equals, and this is on the back of our data booklet, 1.66 times 10 to the negative 27 kilograms. So cancel that out. And I'm going to take this, and I'm going to multiply it by 1.66 times 10 to the negative 27. Right, so now we're in kilograms here. And to finish this off, now that we're in kilograms, to find energy, we just have to go E equals mc squared. So I just have to take that answer, and I have to multiply it by 3 times 10 to the 8 squared. And this is how much energy is released, 2.78 times 10 to the negative 11 joules. So you have to remember that this is per atom, right? So it doesn't seem like that much energy, but if we have a mole of atoms, right? And if you remember, a mole is just a certain number of atoms. So if we have a mole of atoms, it's going to be a lot more, right? Do you guys remember what a mole is equal to? So 1 mole is equal to 6.022 times 10 to the 23. So if I take this energy here, right, this is per 1 atom. Well, if I have 1 mole, and if it was uranium, it'd be like, I don't know, 230 grams would be like one of those big bags of Skittles of uranium, would have this many atoms in it. Right? That's how much energy is given off. That's huge. That's a crazy amount of energy if we're talking about per mole, right? Per certain number of atoms. You wouldn't have to do that mole calculation. We don't do moles in physics. So fission of uranium is a chain reaction. So 1 neutron produces 3, 3 produces 9, and so on, right? So those 3 neutrons are really important because this first neutron splits it, but there's other atoms around. So when it releases the 3, well, this one's going to split this one, this one's going to split this one, this one's going to split this one. That reaction is going to happen a whole time. So this reaction is going to produce 3, this reaction is going to produce 3. So we started off with 1, it turned into 3, it turns into 9, it turns into 27, it turns into, right? It goes on and on like that. And that's basically how you create a nuclear bomb. It's a chain reaction. It just gets bigger and bigger and bigger until all your uranium fuel is used up. So in atomic bombs, the reaction, once began, is uncontrolled and explodes until all the uranium is used up. In nuclear reactors, the reaction must be controlled, and some of those free neutrons must be eliminated using control rods, right? You don't want all your fuel to explode at once, so you got to take away some of those neutrons so that doesn't happen, so it doesn't get out of hand. So the most famous type of reactor in the world, the one that's used the most, is Canadian, which is cool. It's called the CANDU reactor, and it uses uranium fuel rods. So that it uses uranium as a fuel, and it uses cadmium control rods, which are immersed into heavy water. So basically those control rods are moved in and out to increase or decrease the number of those free neutrons, right? So if we want more energy, we have more neutrons. If we have less energy, less neutrons. And when you stick that uranium in water, the water heats up, turns into steam. Right? The steam is shot through turbines, it creates electricity, and once all the fuel rods are spent, they have to be stored and cooled, and there's no way to dispose of them, so that's where you get your nuclear waste. So they just keep them in swimming pools, keeping them cool when they're done with them. So this is how a CANDU reactor works. So you basically have a pool here of water, and then you have your uranium fuel. So this is your uranium fuel rods, and then you have your control rods, which are here, right? So these gray things are our fuel rods, our uranium fuel, and then these are our control rods. So the reaction happens, it gets hot, it heats the water turns into steam, steam turns a turbine. Whenever you have whenever you have a coil of wire moving by a magnet, you induce electricity and you create an electric current, and that's how generators work. So the other type of nuclear reaction you need to know about is nuclear fusion. So when smaller atoms combine to form larger atoms, the reaction is called nuclear fusion. Fusion takes place only under very great temperatures, more than 2 million degrees. So these temperatures only occur naturally in the center of stars like our sun. So stars complete fusion by turning hydrogen into helium. So taking a smaller atom and making it bigger, that's what fusion is. So this is a fusion reaction that happens in the sun. It's a bunch of different reactions, but what you basically need to know is the final reaction here, right? So we're taking hydrogen, we're turning into helium, and we're also creating neutrinos and gamma and beta particles. But hydrogen turning into helium, that's the basic behind fusion. So this chart here shows different bombs that people have used. So this first one is the largest chemical reaction, like TNT. So this is the largest chemical reaction. So if you're making a railway or something, you'd have TNT, you'd explode it as a chemical reaction. The energy comes from bonds. Oops, didn't mean to put that up yet. So this one is very famous. This one is this bomb here, which is called Fat Man. It was dropped on Hiroshima, and then Little Boy or whatever is dropped on Nagasaki. So this is, you can see it's a lot bigger. This one's 1 kiloton, this is 10 kilotons, so a little bit bigger. If you're flying a plane, this is how high the explosion would go, so it would have some effect on this plane. So this bomb ended World War II. And then they're like, what can we do to make a bigger one? So then they made this bomb right here. Oh, right here. This is a fusion bomb. So this is fusion, and this is fission, and this is chemical. A little tiny chemical, right? So this is ended World War II, and then they're like, let's make a bigger one. So then they made a fusion bomb, which is quite a bit bigger, right? So this bomb is Castle Bravo. Castle Bravo was a fusion bomb, and I'll show you a video on that.
Bravo was a hydrogen bomb using solid thermonuclear fuel, confirming the designs of Edward Teller and Stan Ulam, and paving the way to producing aircraft deliverable hydrogen bombs and more effective weapons. significantly exceeding its expected yield by 2.5 times. Castle Bravo, with an explosive power of 15 megatons, stripped islands clean of vegetation and took the scientists by surprise. The huge explosion released large quantities of radioactive debris into the atmosphere. This resulted in the exposure and contamination of some servicemen, natives, and the crew of a Japanese fishing boat, which had gone unnoticed in the security zone around the blast. This incident pushed the dangers of fallout from nuclear weapons clearly into the public mind.
So just a little info on Castle Bravo. So that was real footage from it. So Castle Bravo was a hydrogen or thermonuclear bomb or a fusion bomb that was detonated in March 1st, 1954, Bikini Atoll, Marshall Islands. Not very good, not very ethical with it. They told the indigenous people there that, oh, you gotta leave, we're testing this bomb, and not all of them left, so some of them died, and yeah, not good. So in a hydrogen or thermonuclear or fusion bomb, the same reaction is created in the sun. So to generate the large temperatures necessary, what they do is they create a turducken of bombs. So you need about 1 million degrees for a fusion bomb to happen. So what they do is they place a fission bomb, right, uranium, a fission bomb, inside this hydrogen fusion bomb, and they explode it first. So this, like a Hiroshima, Nagasaki bomb, they explode that first, and then that creates hot temperatures, and then the hydrogen bomb, the fusion bomb, explodes after, and that gives it the heat required, and you get a much bigger bomb when you get this fusion one to go off, right? So the energy released by a thermonuclear fusion bomb is about 10 times the energy of a fission bomb. So way, way, way more energy from that fusion bomb. So with hydrogen, right, all you need for a fusion bomb is hydrogen. So with hydrogen in plentiful supply here on Earth, right, water is made of hydrogen. We have a lot of water on Earth. Fusion could theoretically supply virtually unlimited energy source for mankind. So why don't we have fusion reactors? We don't have any fusion reactors. And the reason why is because they are too hot, right? You need 1 million degrees Celsius for fusion to happen. Okay, so we put we make this nuclear reactor. What do we put it in, right? Nothing can withstand temperatures of 1 million degrees before it starts to melt. So you would have a nuclear meltdown right away. So we don't have the technology for it yet. We are getting close. They are probably about 10 years away from creating a viable fusion reactor. And what they use instead of a container, they use magnetic fields to confine the hydrogen, so they make them ions, and magnetic fields aren't affected by the temperature, so you can keep that hydrogen in there. If you have a magnetic field, you can make it move in a circle, right? And the products of fusion are good, right? The products of fission are those nuclear waste rods that you have to store, and they're radioactive, they're not good. With fusion, you produce helium, and the helium isn't radioactive or anything like that. It's good to go to children's parties to put into balloons. Right? So one thing that you need to know is what gives off the most energy. So if I have a fission reaction, right, where we take this big thing, we split it into smaller things, and if I take this fusion reaction where I take something small like hydrogen, make it bigger like helium, what gives off more energy? Okay. Well, firstly, is it fair to compare this reaction, so I'm burning this match here, with this reaction here, right? What's going to give off more energy? Well, hopefully you're saying the picture on the right, the one that has more matches. More stuff usually means more energy, right? So this is a lot more stuff. It's a lot more protons. It's a lot more neutrons. It's a lot more stuff, right, than this. So if we just look at who gives off the most energy in total, well, it looks like fission is the winner, right? This is fusion. But it's not, going back to these reactions, it's not good to compare these. Which one actually gives off more energy? Well, if one has more stuff, then you're not really comparing it, right? So what would be a better comparison for these two? Well, if we compared how much energy is given off per match, well, then it's going to be the same, right? So if we do it per something, then it's a lot better. So there's two ways that we can look at it. We can look at it in terms of per nucleon, right? So this, if we add these up, this has 236 nucleons, and this, so 4 times 1, so this is 4, so it says 4, right? So if we look at it in terms of nucleons, we would divide this by 236 and divide this by 4, and if we do that, so if we go 177 divided by 236, and we go 24.67 divided by 4, you'll see that, oh, when we talk about it per nucleon, fusion gives off way more energy, right? The other way that we can look at it is per gram, right? This is going to be a lot lighter. Hydrogen is a lot lighter than uranium if you talk about like per mole per number of atoms, right? So if you take this, if we had 1 mole of uranium, it's going to be 235 grams. If we had 1 mole of hydrogen, it's going to be 1 gram, right? So if I take this divided by 1, if I take this divided by 235, again, we find that fusion is bigger. So per reaction, fission gives off more energy, but per nucleon or per gram, it's going to give off way more energy with fusion, okay? You need to know that. So here is a video. You probably won't be able to watch in this video, so I'm not even going to include it. It just talks about nuclear energy, but I always get copyright issues when I post them on YouTube, so I'm not even going to post it. Okay, this last slide here, comparing chemical reactions with, let's do fission first, and fusion. So chemical reactions will give off the least amount of energy, and they get their energy from bonds, right? So this would give off the, let's say, most per reaction, and it gets its energy from mass, right? This gives off most per nucleon and most per gram or kilogram, right? And it gets its energy from mass, right? So an example of this would be burning gas. Right? If you burn gas, it's a chemical reaction. Fission reaction is big to small. So uranium into krypton and barium. And then this one is from small to big. It can be any small to big, right? So it can be hydrogen to helium or helium to lithium. That'd be an example of a fusion reaction, right? I remember fusion as it like fuses small things together. Okay, this is your homework from this. Give it a go. Let me know if you need any help.